So I too would like to thank the organizers for inviting me to give this talk. And my topic is actually somewhat broad, and as you'll see during the course of my talk, I'm actually going to touch on a number of areas that are going to be covered in more depth later on. So in one sense, this talk is actually going to serve as a bit of an overview for some of what you'll hear. So to start with, this is old data just showing in general the relationship between lean mass measured by DEXA and total body bone mineral content. And this is in males, this is in females. I know the slides are somewhat hard to see, but the point I want to make is that there's a generally good relationship between total lean mass and total body bone mineral content. And the other point is that it seems to shift a little bit between pre versus post-puberty. So here it's before puberty, and you can see the solid line is after puberty. And it's these kinds of observations that led to the notion that somehow puberty and sex steroids were modulating these relationships. You see it here also in females. So here in prepubertal females, prepubertal here, postpubertal, and then after menopause, with loss of estrogen, again, there seems to be a shift in this relationship. So fairly old data suggesting these relationships between lean mass and bone mass, and potentially some interactions with sex steroids and how these relationships play out. Now, to try to dissect this a little bit further, Nathan Lebrasser and myself just completed this study, which is now in press, where we looked at our cohort of women and men between the ages of about 20 and 97 years. And because bigger people have more bone and more muscle, we tried to look at these relationships in a way that tried to account for that. So we calculated relative appendicular skeletal mass, or ASM, which was obtained by actually taking the lean mass of the arms and legs by DEXA and dividing that by height. So this was an attempt to circumvent the confounder that bigger individuals will simply have more muscle and bone mass. So you're sort of adjusting to some degree for body size. And we measured volumetric bone density, so size-independent bone density by quantitative CT at the spine and hip. We looked at cortical parameters using standard peripheral QCT, and then trabecular parameters at the radius, trabecular microstructure, by high-resolution peripheral QCT. So this just shows the age-related decrease in relative appendicular skeletal mass. So this is the arms and legs divided by height. And you can see in women, as a function of age, there's a gradual decrease in relative appendicular skeletal mass. Men have higher relative ASM, and it also tends to decrease. Perhaps the slope of the relationship may be even a little bit steeper in the men as compared to the women. Now, if you look at the associations between relative ASM, so height-adjusted lean mass, versus cortical thickness at various sites, here's females, males, this is at the femur neck. At the vertebra, it's really kind of an estimation of the cortical shell in the vertebra, but more robust measures for cortical thickness at the tibia and at the radius. You can see in the women fairly strong, robust correlations between relative ASM and cortical thickness at various sites. I should add that these remain significant after adjusting for age, for physical activity, so these really do appear to be independent relationships between adjusted lean mass and cortical thickness. Similar relationships were present in the males, although perhaps a little bit weaker than we found in the females. What was interesting to us is the relationship between height-adjusted lean mass and trabecular microarchitecture. So this is arms and legs lean mass related to bone volume fraction, trabecular number, and thickness and separation at the radius, which kind of got us to thinking a little bit away from just mechanical influences and potentially other factors that might be regulating this crosstalk. And you can see, just for example, in women, a relationship between relative ASM and the bone volume fraction, actually a stronger relationship between relative ASM and trabecular number, and also here with thickness, and similar associations present in the men. Now, to try to understand some of the determinants of this, we looked at a number of variables, including sex steroids, IGF-1, IGF binding protein 3, and other components of the IGF system. It turned out that the most robust negative regulator of both muscle and bone mass, and here are the data for muscle, turned out to be IGF binding protein 2. So this shows the relative ASM. This is in women and in men. And you could see a negative association between IGF-BP2 and relative ASM. So as IGF-BP2 levels go up, relative ASM goes down. This is in women and this is in men. This was of interest to us because a number of years ago, we had seen very similar relationships between IGF-BP2 and bone density at a number of skeletal sites. So here, for example, in postmenopausal women, the correlation between IGF-BP2 and hip BMD was negative, similar to what we see for the relationship between BP2 and muscle mass. So the fact that here was a biomarker in serum that was related in very similar ways to bone mass at multiple sites, but also to muscle mass, was really of great interest to us. So to summarize this data then, skeletal muscle mass relative to body size is significantly associated both with cortical and trabecular bone geometry and microarchitecture at multiple skeletal sites in adult women and men. That IGF-BP2, a factor whose circulating concentrations we previously reported with low BMD and high bone resorption markers, was also associated with low relative ASM in both sexes. The relationship, we thought, of relative ASM to cortical parameters could perhaps be explained by mechanotransduction, thinking that cortical sites are right next to muscle and there may be direct influences of the muscle on cortical bone. But what was of interest to us is the relationship of relative ASM to trabecular microstructure may provide evidence for either osteokines or myokines that are secreted factors and therefore influencing muscle, influencing bone perhaps at some distance from the direct surface interactions that might be occurring on cortical bone surfaces. It was interesting that IGF-BP2 may coordinately regulate skeletal muscle and bone, and there are several potential explanations for this. We know that IGF-1 and IGF-BP3, which is often used as a biomarker for growth hormone secretion, that both of these decrease with advancing age, while IGF-BP2 levels, in fact, increase fairly substantially with age. BP2 is generally considered an inhibitory binding protein for IGF action, so one reason for this negative association with bone and muscle mass could be that it's a global inhibitor of IGF action under these conditions. However, it's also of interest that independently IGF-BP2 has been identified as a component of the senescence-associated secretory phenotype, and it's increasingly believed in the aging biology community that this may be a fundamental driver of age-related tissue dysfunction. In fact, another paper that Nathan was involved in with Jim Kirkland and Jan van Dersen at Mayo came out last year showing that at least in a progeroid mouse model, accelerated aging model, that you could delay multiple aging phenotypes by killing off senescent cells. So there may be a tie-in between BP2 and reflecting total body senescence. It turns out also that higher BP2 levels have been linked to osteoporotic fractures and with poor physical performance and disability in older men. So this may be providing us an interesting clue. What the precise mechanism for this remains to be defined. So let me turn now from kind of these associations to try to understand, or at a clinical level, to provide a framework for some of these interactions between bone and muscle. And for this, I think you really have to go back to some of the seminal concepts of Harold Frost, and he published a number of review articles relevant to this. And I think this is something, as we go through this meeting, his kind of concepts that were developed many years ago really need to be kept in mind. This is a schematic which really summarizes his mechanostat theory. So what this says is when you're above the line, you'll have bone gain. When you're below the line, you'll have bone loss. And these are various thresholds. So this is the remodeling threshold. So when you go from normal physical activity to complete disuse, as in spinal cord injury or immobilization, that you're going to really trigger this remodeling threshold where you'll get marked bone loss. And we do, in fact, see that with prolonged bed rest or spinal cord injury, as I mentioned. As you get to higher loads, you get into this modeling threshold, which is this mild overload, where you're straining the skeleton to a certain degree and gaining bone in this range. If you go too high, you get into a pathologic overload situation where eventually you may fracture. But of particular interest to this talk is this mild overload modeling threshold, because it's really believed, or Frost believed, that, and this was really echoed by further work by Mike Parfit and others, that it's in this area of mild overload that we really gain bone mass during growth and development and during puberty, and the role potentially of muscle muscle might play in this. So there are various ways to test this in humans. The limitation, of course, is that what I'll show you is largely correlative data. There really isn't direct interventional data to test Frost's mechanostat ideas. So until you develop, animal models or mouse models to directly dissect this, you have to rely on the observational correlation studies. But I'll try to summarize kind of the state of the art there. This, I thought, was a very important and interesting paper by Frank Rauch, and actually Mike Parfit in that issue of Bone wrote a beautiful editorial to this about his kind of interpretation of this fundamental test of Frost's mechanostat theory during growth. So the idea is that the mechanostat theory that I just reviewed with you predicts that the increasing muscle mass and thus the muscle force during growth should create the stimulus for the increase in bone mass and thus in bone strength. So if this was really true, then when you looked at this longitudinally, the increase in muscle development must precede and should determine the increase that you see in bone mass during growth. So to test this, Drs. Rauch and colleagues studied 70 boys and 68 girls aged 8 to 14 in a longitudinal study. And they measured DEXA scans annually to look at bone and muscle parameters. Now, this is a complex slide, but I'll kind of walk you through it. So what this shows is the velocities of total body lean mass and bone mineral content accretion. So here's total body lean mass velocity or bone mass velocity. So this first curve, which is in yellow, shows the lean mass velocity. So you can see this dashed line is when these males are achieving peak height velocity, when they're having most rapid longitudinal growth. And this is where the increase in lean mass peaks. And you can see, followed by this is the changes in total body bone mineral content. So again, consistent with the kind of the mechanostat idea, the increase in lean mass is preceding the increase in bone mass, the peak increase in bone mass. And you see a very similar pattern in the females, where again, here's the increase in lean mass, and then somewhat later you see the increase in bone mass, and this is relative to peak height velocity, which is somewhat sooner in women or in girls. So to look at this kind of more rigorously, they noted that the peak in total body peak velocity for lean mass preceded the peak in total body peak velocity in bone mass in both sexes by an average of about 6 months in girls and a little over 4 months in boys. Total body peak velocity for lean mass occurred before total body peak velocity in bone mineral content in almost 90% of the girls and about 80% of the boys. And then they tried to build multiple regression models that tested sex, peak height velocity, and total body peak lean body mass velocity as predictors of peak bone mineral content velocity. And basically this showed that only the peak velocity for lean mass was independently associated with total body peak velocity for bone mineral content. So again, correlative data, but consistent with the idea that during growth, the increases in muscle mass peak before the increases in bone mass, and again, raising the question of whether one, in fact, is driving the other. Had the opposite been found, there would be, I think, a strong reason to doubt the mechanostat idea, but so this is certainly consistent with that notion. Now, in a subsequent study, Zhu and colleagues looked at potentially the hormonal determinants of bone and muscle growth, and I thought this was a really interesting study because they used, again, it's still correlative, but they used hierarchical models to evaluate the associations of IGF-1s and sex steroids with peripubertal bone growth in a 7-year longitudinal study. For this, they looked at 258 healthy girls that were assessed at baseline at mean age of about 11 years, and then up to 7 years thereafter. And they measured musculoskeletal properties in the left lower leg using peripheral QCT. This just shows the changes in IGF and sex steroids. This line represents menarche, so this is before the onset of menses. After the onset of menses, you can see IGF-1 during growth peaks right or soon after menarche and then declines rapidly afterwards. This is estradiol, which again peaks around the time of menarche and then remains fairly stable. Girls do have low androgen levels, obviously relative to boys, but there's a gradual increase throughout puberty in androgen levels and testosterone levels in the girls. So again, when they looked at the associations between the hormones and bone variables, and their main outcome was periosteal circumference, again, because this is such a driver of bone strength. So in one model, they included IGF-1 and the sex steroids, and you can see here that testosterone, both before and after menarche, as well as IGF-1, were important predictors of bone size or periosteal circumference, so suggesting that both androgens and growth hormone, potentially growth hormone-driven IGF-1 was driving periosteal circumference. But then they did something interesting. In a second model, a statistical model, they included muscle cross-sectional area. So as soon as you put muscle cross-sectional area into this model, it becomes a significant predictor of periosteal circumference, and IGF-1 drops out. So based on this modeling, they drew some, I think, fairly interesting and intriguing conclusions that, again, set up hypotheses that can be tested either in interventional studies or in animal models. And so basically their conclusion was that during puberty, circulating IGF-1 in fact promotes bone periosteal apposition and mass indirectly, probably through stimulating muscle growth. And they based this, as I mentioned, on the idea that once you let muscle cross-sectional area into the model, the IGF-1 effects disappeared. So a logical conclusion would be that the IGF effect is in fact through muscle, although again, this is still correlative. Now, you'll hear later in this talk about the role of genetic factors, and obviously an obvious question is, are muscle and bone related simply because there are common genetic determinants for body size? I mean, we attempted to adjust for effects of body size by adjusting for height, but are there a common set of genetic determinants for both muscle mass and bone mass? And I think this was an interesting study done by Igor Seaman, kind of a typical monozygotic and dizygotic twin pair study, where they measured the extent to which the association between lean mass and bone mass was determined by genetic factors or by environmental factors that are common to both traits. So the idea, again, being that with dizygotic twins, you're going to share common environmental factors, but you're going to have less, obviously, common genetic factors than with monozygotic twins. So this just shows the twin pair associations for bone density. Here's at the femur neck, lean mass and fat mass. And you can see there's strong genetic determinants. So here's monozygotic twins. You can see the relatively good correlation for femoral neck bone density between twin pairs. This is for lean mass. Actually, it's fairly tightest for fat mass in the monozygotic twins. It's less strong in the dizygotic twins. There is an association, but it's much less strong than in the monozygotic twin pairs. So this was an interesting analysis that I think tried to get at this. And what they did was look at trait correlations and cross-correlations between bone mass and lean mass. So I'll just kind of walk you through one example. So if you look at lumbar spine, and the correlation between lumbar spine bone density and lean mass in the same individual, that's the correlation coefficient. But if you look at the lumbar spine BMD in one twin correlated with lean mass in the other twin, that's this correlation. So this is in the monozygotic twin pair, and this is in the dizygotic twin pair. So what this says is that if you look at the correlation between BMD and lean mass, it's actually pretty, fairly significant even in the other monozygotic twin, and then you lose a lot of that in the dizygotic twin. And so based on this kind of analysis, Ego and colleagues suggested that the proportion of the covariance that's attributable to genetic factors could be anywhere between 55 and 85%. If you just took the ratio of this to this, on average, it was about 55 to 85%. And they kind of came up with this model where if this is the overall variance in BMD, this is the overall variance in lean mass, this is the proportion of the BMD variance due to genetic factors, and this is the proportion of the lean mass variance due to genetic factors. And this kind of represents the overall covariance of lean mass and bone mass, that up to 50 to 80% of that covariance is probably driven by genetic factors. And what those genetic factors are, I think, is a really important question that remains to be defined. So in the final few minutes of my talk, I'm going to come back to kind of Frost's idea and the notion that I introduced earlier about the interactions between this mechanostat and sex steroids. So Frost actually had, I think, a very clever formulation of bone loss following menopause. So what he postulated was that before menopause, there's a certain amount of bone mass that puts a certain amount of strain on a strain generator. Now, you know, what this strain generator and what this mechanostat is, he didn't really articulate that, but probably the leading candidate for that today is the osteocyte, particularly this mechanostat. And the idea was that this strain is sensed by this mechanostat, that if there's too much strain on it, you know, if this is positive, then it's going to trigger bone gain. If it's negative, it's going to trigger bone loss. If the mechanostat senses there's too much bone, it's going to trigger bone resorption. And there's some kind of strain signal going to this mechanostat. So Frost's central idea on this was that estrogen regulated this mechanostat. So when you became estrogen deficient, for the same amount of bone, the mechanostat was sensing that there's too much bone. So it went into kind of a negative strain and triggered bone loss, and that's how he felt postmenopausal bone loss was triggered, until you lost enough bone that you started to put more and more strain on the bone, and you came back to a new steady state, but with lower bone mass than you started off before the menopause. So the central idea, though, was somehow estrogen was regulating this mechanostat and potentially the osteocyte, if we believe that that, in fact, is the mechanostat. Well, there is evidence from this. Lance Lanyon and others have done a lot of work showing this interaction of estrogen signaling with mechanical loading. This is in mice, either the control or loaded limb. And you can see in wild-type mice with loading, there's an increase in cortical area in the limb that was loaded. If you knock out ER-alpha, these are global knockouts, you can see a marked decrease in the increase in cortical area in response to loading, and you actually see a modest decrease with knockout of ER-beta. But this was one of the original studies by Lanyon's group showing that ER-alpha, and it turns out in these studies it's probably unliganded. It doesn't even have to be liganded, that even unliganded ER-alpha modulates the interaction between mechanical loading and the increase in bone mass that you see. This has led to this kind of concept that, you know, when you look at the relationship of lean mass to bone mass, and I kind of alluded to this at the beginning. So here's lean mass, whole body BMC. So here's boys, you can see a fairly linear relationship. Here's girls until they hit menarche, and suddenly there's a fundamental shift in this relationship. And this has been attributed, this kind of data, again, back to Lanyon's data and Frost's idea that somehow these high estrogen levels that are achieved after puberty in girls are modulating this relationship between lean mass and bone mass, and potentially this mechanostat that's present in bone. Now, at a more clinical level in adults, this was a nice paper from Jean-Marc Kaufman where they looked at male siblings aged 25 to 45 years. They looked at physical activity assessed by a self-reported questionnaire, and obviously more sophisticated measures of physical activity are needed and would be helpful in this type of analysis. They measured musculoskeletal parameters by PQCT and sex hormones by immunoassays. And just to briefly summarize a complex data set, they looked at the interactions of physical activity and estrogen on bone parameters in men, and these are the beta coefficients of their statistical models. But the point I want to make is that if you look at a number of these variables, for example, cortical bone area, there was a statistically significant interaction between the free estradiol level in the men and physical activity in terms of the impact of each of these on bone area. Again, consistent with the notion that sex steroids were somehow modulating the effects of physical activity on bone, and you can see it for a number of these cortical parameters that they measured by PQCT. So I'm going to close by summarizing my talk, which is that I hope I've convinced you that the association of appendicular skeletal mass adjusted for height with bone geometry and microstructure is consistent with an underlying association between bone and muscle that's independent of body size. This relationship is likely, at least in part, due to mechanotransduction, but we believe that the associations with microstructural parameters are harder to explain simply by mechanotransduction and really speak to a role for potentially bone-muscle crosstalk through osteokines or myokines. That during growth, again, consistent with this relationship, the peak velocity for lean mass does precede that for bone mass, which is really consistent with the mechanostat idea that increasing muscle mass during growth creates the stimulus in part for the increase in bone mass. That during puberty, circulating IGF-1 may promote bone periosteal apposition, but this effect may actually be indirect through actually stimulating muscle growth. Conversely, during senescence, rising BP2 levels are associated both with declining bone and declining muscle mass. Twin pair studies suggest that a fairly high proportion of the covariance of bone and muscle mass is likely genetically determined, and what those genes are obviously is of great interest. And certainly animal and correlative human data are consistent with Frost's notion that during growth and aging, estrogen in fact regulates the sensitivity of this mechanostat. And how that occurs at a cellular or molecular level is obviously of great interest. So we were each asked to come up with our key questions. So in my mind, they are, what are the underlying genetic, hormonal, and environmental factors that determine the covariance of bone and muscle mass? We know they're correlated, but what are these factors? Is the bone-muscle relationship explained largely by Frostian mechanotransduction or by osteo or myokines, and what's the relative contributions of these two factors to driving this relationship? And is the osteocyte truly the only mechanostat, or are there others? And how does estrogen modulate at the cellular level the relationship between muscle loading and bone? So I'm sure there are others, but these were the key ones that I was able to come up with. I wanted to acknowledge my colleagues in this work, particularly Nathan Lebrasser, who's here, who did the study with the peripheral QCT parameters, and then support that we received both from NIA, from NIAMS, from the Mayo CTSA, and Mayo Foundation. Thank you.
Nicholas, San Francisco. Sundeep, nice talk. I want to put a twist on the IGF-1 story and during your pubertal growth. So in mice, when we work with our IGF-1 receptor knockout animals in the mature osteoblasts and therefore osteocyte, what we see with mechanical loading, let's say going from the unloaded to the reloaded situation, is that when you knock out the IGF-1 receptor in the osteoblasts, they in fact don't respond to the reloading, suggesting that if we do have this interesting crosstalk between muscle and bone, and I think you're right on, it may be that it's the IGF-1 coming from muscle, which in fact is affecting the IGF-1 receptor that's in the bone.
Sure.
Interestingly enough, the endosteal surface and trabecular surface in this animal model responds perfectly well to reloading. So there is something very interesting about the periosteal bone interacting presumably with these mechanical forces in muscle, and why not IGF-1?
Sure. Yeah. Thank you. I think it's really interesting kind of relationships between how IGF might work on muscle versus bone. Yeah.